Now let's go to our region D and identify the region of operation for my NMOS and PMOS. So in region D, my input is equal to VIH, which means input is high. If input is high, my output is going to be low. Let's start with NMOS transistor first and identify VGS-VT. VGS is nothing but Vin, which is equal to VIH, which is high, so nearly equal to VDD, which will be greater than threshold voltage, which is nothing but 0.7. So my NMOS transistor is on. Now what we need to identify is whether my NMOS is operating in linear region or in saturation region. Let's quickly do that. VDS dash VGS minus VT. VDS is nothing but V out. VGS is nothing but V in minus VT. Output is low. Input is high. It's a clear case of less than sign, which says that my NMOS transistor is operating in linear region when my input voltage is VIH. Let's quickly do the same for PMOS and identify the region of operation. So first let's identify whether the transistor is on or not. VGS dash VTP. Gate voltage is nothing but VIH minus the source voltage, which is nothing but VDD dash VTP, which is nothing but minus 0.7. VDD is 1.8. Now here is an interesting thing. The definition of VIH is it is the minimum input voltage which will be considered as logic high. So if I have a range from 0 to 1.8 and if 0.9 is the point where below that is considered as logic 0 and above that is considered as logic high, then VIH is somewhere around 0.95 or 1 volt. So let's assume here as 1. So 1 minus 1.8 is minus 0.8, will be less than minus 0.7. So this clearly shows that my PMOS transistor is on. What we need to identify is the region of operation, whether it's in linear or in saturation. Let's really do that. VDS for PMOS is nothing but V out minus VDD. VGS is V in minus VDD minus VTP. VDD gets cancelled. Input high, so output is low. Input is high because we are trying to find input high VIH. This clearly shows that this is a less than sign, which means that my PMOS transistor operates in saturation region. So for region D, when my input is equal to VIH, my NMOS transistor is in linear region and my PMOS transistor is in the saturation region. And because my input is high, my output voltage is going to be low, approximately equal to output low, which is nothing but VOL. So that completes the fourth case. Now let's quickly go ahead and let's take the last case. Last case is when my input is greater than VDD plus VTP. Let's start with NMOS. VGS, which is nothing but V in, which is nothing but VDD plus VTP, which is nothing but 1.8 plus VTP is minus 0.7 technically, so this is nothing but 1.1, which will be greater than the threshold voltage, which is nothing but 0.7. So my NMOS is on. What we need to identify is whether my NMOS operates in linear region or in the saturation region. Let's quickly do that. VDS is V out, VGS is V in minus VT. Because my NMOS is on, we know that the output would be pulled down to a logic 0. So output is close to 0. That clearly shows that input is high because it's an inverter and it's going to be a less than sign. So my NMOS operates in linear region. Let's quickly see what is the situation with my PMOS. For PMOS, let's write VGS, which is nothing but V in minus VDD. V in is nothing but VDD plus VTP. It's greater than this, and minus VDD. So VDD gets cancelled. Remember, this is greater. So greater VTP dash VTP is always going to be a greater than sign because this is what it's given. V in is greater than VDD plus VTP. So if it's a greater than sign, it clearly shows that my PMOS transistor is in cutoff. So in the fifth case, we saw that my NMOS transistor is operating in linear, my PMOS transistor is operating in cutoff, and because my NMOS is on, my output is pulled to a logic 0 or low output, which is nothing but Vout equal to VOL. This completes all the regions of operation, and now we will see a voltage transfer characteristic depicting all these 5 regions. Stay tuned for further clips on the graph on the CMOS inverter or the voltage transfer characteristic of a CMOS inverter. Thank you.